Okay, so if we turn our attention to the next function we're going to try and implement using test-driven development, we can look at the set function, and we're trying to set a specific index of our vector. And so if we initialize our vector in this test with one element or a capacity of 1, we should have enough space in our buffer for one int16 value. We're going to set up a local value here, and we're going to call the vec set function, giving a pointer to, or the address of, the vec. We're trying to set index 0, and we're giving the set function the address of this x variable so that it can copy the bytes from this x variable into the buffer of the vector. And after we call set, we expect that the length of this vector should be 1. You know what we should probably do is we should probably also, I'm going to copy this line with yy. Before we do anything, we should assert that the value is initially 0, so the length is initially 0. But by setting the index 0, we expect that its length will be updated to 1. And then just like using a trick we did before, but this time around we're trying to verify that the data was properly copied in. If we take a pointer and we recast our buffer to an int16 type pointer, which is what it actually is underneath the hood, then we should be able to assert the equality of this x value and the buffer at index 0. So we expect it to be equal to 1, and then we drop our vector to free up the memory afterwards. Okay, so we have this is about as simple of a test as we can imagine, right? We're trying to just try setting the very first index is 0, see if we can get this to work. And I've got a skeleton implementation of the function here. It's a void function, so a void function, we don't need to return anything for this to compile, and we can try and make unit test to see if it does. All right. So we'll see that this fails, as you can expect, because it does nothing, right? So this failed. It expect length to be 1, but it was 0 after calling set. So we have some more work to do. Well, what do we need to do here? The first thing we need to do is talk a little bit about this void pointer business, right? So this is something that came up in the last lecture where you wrote a copy function that copied some number of bytes from one pointer that was void to another pointer that was void. And we're going to be making use of that exact same functionality here, right? It turns out there's a standard library function called memcopy built into the string library, which is in a part of GCC, and we can look at its implementation here. So memcopy is exactly the function you wrote in the last lecture to copy some number of bytes length from some source pointer that's a void pointer to some destination pointer, right? And so this might be a little bit more terse than the code that you wrote, but effectively it does the same thing, right? We're saying while length minus minus is greater than 0, so we go from the current length index down, or we go from the current length down to 0. And as we do that, what we're doing is we're copying the byte at we're copying the byte from pointer s, because it's a char pointer, that's our source, to the address of d. And remember, the plus plus in each of these gets evaluated after the fact. So after that copy happens, then we increment each of those pointers to be 1 byte beyond where they were. So you may have done this in a slightly different way, but this is effectively just copying all the bytes or length number of bytes from source to destination and ultimately returning the address of the destination. So we're going to use memcopy to copy blocks of memory from the value that we're trying to set, right? So the value that we're trying to set is here, and we know that this value, by virtue of the contract that we're applying to this, if this is a vec of int16s, we know that that value is going to be 2 bytes, and that will be stored in the item size member of my vec struct. And then we're trying to copy that to this given index, right? So let's just try a very naive implementation here. So a naive implementation would be, we're going to call memcopy. And where are we copying this to? Well, we're copying it to self buffer, right? That's index 0. And we're copying the from the value, that's our destination, or sorry, that's our source pointer. So buffer, self buffer is our destination and value is our source. And then the number of bytes we're going to copy is self item size, right? And so what this will do is this will copy item size number of bytes. In this test case, that's 2 bytes because we're dealing with an int 16. From the value pointer. So the value pointer will be what we got the address of in our test to this buffer, right? Now, this is a very naive implementation, but let's see if it works. Hopefully you're already expecting that we still have more work to do for 2 purposes, right? So this test doesn't work. It says that the length is expected to be 1, but it's still 0, right? So we didn't update the length of this vector by virtue of doing this, right? So the simplest way to pass this test, again, if we're just trying to follow sort of a brute force, pass the test mindset for now, would be to say self length is 1, right? Make unit test. And so let's see if this passes our test. And sure enough, it does, right? So this passes the most basic test we could form. But you have to be thinking, wow, this really doesn't seem like a robust implementation of set at all. This is only going to work if we're looking to set the index 0 element, and we're never going to set an index past 1. Right? So we still have some more work to do here. And what I want to try turning it over to you to do is adding another test for set that's a little bit more robust and seeing if you can implement set such that it would pass that more robust test and work more generally. All right, so let's try doing this together. I'm going to copy my first test here and paste. And I'm going to do 2 things to make this a more robust test. First, I'm going to leave the value that we initialize this with just a length of 0. And I'm going to try adding another int 16 value here. So y is 2 and vec set address of v at index 1, and we're giving the address of y, right? So we're trying to copy the contents of y into the vec v at index 1. And now this is going to be beyond the initial capacity. So we better hope that we're properly ensuring the right capacity of our vec after that. And then what we're going to do is assert equal y to buffer index 1. Right? And so that's going to test the actual contents there. I should also be sure that my length is properly updated, right? So my length is going to be 2 after this. And we need to give this test a different name. So set to elements or items, I'll say. All right. So this is a more robust test than the first one. So let's see if we make test here. We should expect to see that we're now failing this test, and that's good news. That means we still have more work to do on the implementation, but we have a test that is more robust than the first test that we wrote. And sure enough, here we expected there to be a length of 2, but the length was still 1 because we're hard coding in that length, right? So we obviously still have some more work to do here. Well, there's a few problems, right? Let's try and address these one by one. So one problem is the address that we're copying to is always at the start of the buffer, but we really want to be copying to the specific index in that buffer that's at the correct offset. We've already implemented this functionality or this vector or pointer arithmetic in the ref function. Okay, so let's make use of that. So we're going to say vec ref self index. Okay? And so that's going to say, okay, we're going to copy the destination of this mem copy, right? Where we're going to copy the bytes from value to some destination is going to be the correct index. And we've already tested this, this implementation, so we have some confidence that that arithmetic is correct. And we're avoiding duplicating that arithmetic if we ever wanted to change this in some way. Okay, so that seems good. Length, we still have some problems with, so we're going to need to rethink length. Length might not always grow in this case, right? So we're going to come back to that. But before we worry about length, let's worry about this other issue of we initialize this vec to be able to hold one element in it or one item, but when we added the second item, we're going to need to grow our vec, right? So earlier in today's lecture, you looked at the ensure capacity function, and if we give it the pointer to ourself, what we want to ensure here is that we have enough capacity to store what? Well, we need to think about an edge case, and we're not going to have all of the error checking that you'll have in the lab here. We're going to take a naive approach in this video. But let's think about the naive approach, and let's just say we need to ensure the capacity of index plus 1. Right? So what's the logic of index plus 1? Well, if we imagine that we currently have a capacity of 0 and we're asking for index 0, then we would ensure that we have a capacity of 1, which would be enough to store the value we're about to add to it. If we then asked for, say, index 10, and we previously had only capacity for 1, we would here be asking for a capacity of 11, because index 10 would imply starting from index 0 all the way up to index 10. That means we need a capacity for 11 and so on and so forth, right? When you actually go to implement this in the lab, we're going to enforce some rules that would prevent you from having empty uninitialized areas of your vec, right? So we'll have some additional logic that prevents you from creating or from setting any value beyond the maximum index that's currently exists in the vec. But for now, this will be fine. So this will grow our vec. Okay, so we still have some more work to do. We still need to update the length of our vec if we just added to the end of it, right? So we're gonna just take a quick and dirty approach here. You'll want to clean this up in the lab implementation, but if index is greater than or equal to self length, we want to set the length to be index plus 1, right? And again, the rationale here is we've got this off by 1 because we're starting from an index 0. The length is always going to be 1 more than the maximum index, and we just ensured, as we wrote to the maximum index, that it would be 1 beyond the index the length would be 1 beyond the index we asked for. So we can try running this, make unit test. And after our test compile and run, we should hope to see that we're now passing this slightly more robust test. And sure enough, vec of set 2 items is passing, right? So we might add some more tests here. You can imagine maybe we try having the size double, and we can imagine making our implementation a little bit more robust. We actually, in the lab, are going to have you error out if you write to an index that doesn't yet exist and is more than 1 beyond the current maximum index. But for now, this is a fine implementation.